So when Rafi came to the lab of Alex Levitsky, it was like 7 years ago, a little bit more, where I did my PhD in experimental biochemistry, I couldn't understand what he's talking about. But then he didn't want to give up, and then at a certain stage I decided also not to give up. And then step by step we found a common ground. And today I'm going to tell you how surprisal analysis can be implemented in the field of personalized medicine. So currently we are unable to predict a change in pathological processes. For example, we don't know how a particular patient will respond to treatment or which resistant mechanisms or processes will occur. So we suggest that the approaches based on physical rules may allow us to identify those processes. So we suggest to implement surprisal analysis that allows to predict a change in non-equilibrium systems, including biological systems. So in biological processes, we characterize the main components of those processes, protein networks, that in many times work under constant temperature and pressure. In every system or in every patient, we identify the most stable state of the system, the steady state. Steady state in biology is a state in which outputs and inputs are balanced and metabolites are consumed and generated in equal rates. This is actually the most natural point for applying of thermodynamic-based principles. We also identify the perturbed or constrained states that deviate the system from the steady state due to certain constraints, like any environmental change or genomic change can be considered as a constraint that prevent from the system to reach the most stable or homeostatic state when we talk about patients. So in biology, we recognize the constraints by identifying how the protein distribution levels deviate from their expected distributions at the steady state. So all the proteins that deviate from the steady state in a similar manner are organized into groups or networks. So in biology, we identify unbalanced processes that operate in the system. For example, recently we have shown that a surprisal analysis of protein expression levels in two communicating cells allows us to identify a cell-cell separation distance in which the signaling is most stable. And that stability actually dictates spatial distribution of brain cancer cells. We also have shown later that an accurate identification of unbalanced processes allows us to predict a change in cell movement. So now we extend this approach to the field of personalized medicine. So today then, when two patients came to the hospital, if they show similar blood or tissue tests, they will probably be assigned the same treatment. But one patient will respond well to treatment and another will develop resistance. This may happen because additional processes may occur in cancer tissue that usually are not taken into account by conventional methods. So I will give you a simple example. So a conventional method today includes a measurement for a very short list of biomarkers or proteins which are usually involved in cancer development. For example, in this case, let's say a clinician measured 4 different proteins and he found that 3 of them were induced, overexpressed. And let's say from the literature we know that protein B is regulated by protein A. So in this case, a clinician may suggest a combined therapy which will reduce proteins A and C if it's, of course, approved by FDA, this combination. But the situation can be much more complicated. This protein B can indeed participate in the process, in which also the protein A participates, but it can also be involved in another process which we missed. Additional processes may be missed in clinics. So we suggest that in order to design patient-specific drug combination, we need to resolve all unbalanced processes operating in the tissue, and for every single protein, we need to understand in which processes it participates. So to validate this idea, we have recently analyzed a big data set of more than 3,400 different tumors from different 11 anatomic sites. Every tumor was profiled for 181 central proteins which are involved in cancer development. So when we analyze big data sets, we actually examine variations in protein expression levels. So if a particular protein is not involved in any of unbalanced processes, its distribution will be close to normal. But those variations may also arise due to a particular constraint which we want to identify. If we want to identify additional proteins that participate in the same constraint or unbalanced process, okay, we build protein-protein correlation maps. When we want to identify all the proteins which are correlated or anti-correlated in a similar manner in this unbalanced process, we calculate covariance matrix. We use this matrix in order to fit between the experimental levels and the theory. And briefly, in the theory, what we do, we decompose protein expression levels into the expected levels at the steady state and due to unbalanced process in which every protein participates. And every single protein can participate in one or more, as indicated by sigma, unbalanced processes. So why it's very important? Let's say a change in a particular protein is 200. So we need to identify the process that contributes the most to this change. Let's say the process number 1, process 2 contributes less to this change, and process 3 does not contribute. And again, the importance of this is illustrated here. For example, phospho-AKT and phospho-EGF receptor are induced in both cancer patients. But here, phospho-AKT can be induced due to one unbalanced process, whether here, phospho-AKT can be induced due to 2 different unbalanced processes. So if we will inhibit phospho-EGF receptor here, the activity of phospho-AKT will not necessarily be inhibited because additional process is active in that particular patient. Therefore, a very accurate identification of the patient-specific unbalanced network or network structure is essential in order to suggest patient-specific drug combinations. Recently, we have shown that indeed 2 different patients may have similar expression levels of certain biomarkers, but have very different cancer biology because of very different molecular networks. So let's go back to the data set. So we analyzed this huge data set, and what we found that this data set could be characterized by only 17 unbalanced processes that may sound very simple. I will give you example for the process, what I mean by process. For example, let's look at those oncoproteins or main players in cancer. This process, for example, EGF receptor, which is one of the main players in cancer development. Here, it is connected to many other proteins, but it's not connected to phospho-AKT, which is another main player in cancer. In the process number 4, both proteins are induced and correlated. In the process 5, phospho-EGF receptor is induced, and phospho-AKT is reduced relative to the steady state. We found also that every tumor could be characterized by a set or a subset of 1 to 4 unbalanced processes out of 17. So you can imagine that actually thousands of different combinations of 1 to 4 processes can be assembled out of 17 unbalanced processes, which is in line with huge heterogeneity of different cancers. Now I will give you an example for 2 different patients. For example, this patient is characterized by a subset of the process 1 and 5. So if you look at experimental levels of 2 proteins, AKT and EGF receptor, the induced level of phospho-EGF receptor can be attributed due to the processes 1 and 5 in which this process is induced, and reduced level of phospho-AKT due to the process 5, which is anticorrelated with phospho-EGF receptor. In another patient, the induced level of phospho-EGF receptor is attributed now to a different subset of those processes, process number 1 and 4, and the induced level of phospho-AKT due to the process 4. So based on those combinations of different processes, we can build a barcode for every single patient, and based on the central players in every unbalanced process, we can suggest a patient-specific therapy, which in many times actually includes drugs which exist already in clinics. So even though many different combinations, thousands different combinations can be assembled out of those 17 processes, as I said earlier, we found that actually 452 different barcodes repeat themselves in this huge data set. So actually, instead of 11 different diseases, we have 452 different cancer diseases. So to validate this approach experimentally, we tested 10 different cell lines. This is actually tumors that you can grow in lab. Those cell lines were treated with natural ligands or drugs. So our final data set included 60 different samples, for which we found 8 unbalanced processes. To test experimentally further, we chose 3 different cell lines, and I will explain briefly what those cell lines mean. Those 2 cell lines actually represent triple-negative breast cancer. This type of cancer in clinics does not have any biomarkers, and usually there is no targeted therapy that can treat this cancer. In clinics, usually women receive cytotoxic drugs, chemotherapy, for example, Taxol. This type of breast cancer represents a cancer that usually is treated with tamoxifen in clinics, meaning that this type of cancer expresses estrogen receptor. So every single cell line was assigned a barcode, as I have shown previously. For example, this triple-negative breast cancer cell line was characterized by 3 unbalanced processes that actually could be targeted by 2 different drugs, doxyglucose and trametinib, according to the analysis. So again, this is the signaling signature that we identify in those 2 drugs as were predicted by the analysis. And as you can see here, when we test every single drug alone, which is trametinib and deoxy here in light blue and yellow, every drug does a nice job in killing the cells, But when we combine 2 drugs together, and this is the predicted combination by surprisal analysis, we achieve a very nice killing, And what is very nice, this treatment is much more effective than Taxol. Taxol, this is the drug used in clinics today to treat those patients. At a certain point, this drug reaches plateau, so just cannot kill more than 20% of the cells, while our combination did much better job. And so here we wanted to show that the cell death is through apoptotic machinery. That's why we measure cleaved PARP here in this case. When we move to another triple negative breast cancer, we find absolutely another picture. This cancer cell line was characterized by 5 different unbalanced processes. And at first we were very brave and we tried to capture all those processes by only 2 drugs. It was erlotinib and trametinib, okay? Here. And so indeed you can see, for example, when every single drug does certain job, it kills around 50% of the cells, the combination works much better. But here we had a problem. Taxol, in this case, killed more cells. So, okay, we went back to the analysis and we looked for another target that could be useful in our case. So when we added additional target according to the analysis, which was tamoxifen, you can see here the comparison. It did a great job, much better than 2 drugs, the combination of the 2 drugs, and also much better than Taxol. So here, in this case, as I said earlier, usually this type of cancer is treated with tamoxifen, but using the analysis, we suggested that if we add additional 2 drugs to tamoxifen, which is used in clinics, it should work much better. And here you can see indeed our combination works much better than tamoxifen alone, and also than Taxol used in clinics. So now I'm going to show you not a very nice picture, but it's actually a very important one, because we show now on the organismal level that an analysis actually does much better work than the drugs used in clinics. What you can see here, that for example, when we add Taxol and try to treat mice, the tumor continue grow, okay? And when we add the predicted by our analysis drug combination, we stop tumor growth. So to summarize the talk, actually when we take a very big data set that continue many different patients and reduce this huge data set to allow dimensional space, in our case it was like only 17 dimensions, it allows us to construct patient-specific set of unbalanced networks. Then using those unbalanced processes, we construct for every single patient-specific barcode. This barcode guides us in the design of patient-specific drug combinations. And in more general sense, surprise analysis allows us to take multiple variables to reduce everything to a small number of physical parameters. Those parameters allows us to predict a change in many biological processes. And thank you very much to Rafi for introducing me to this magic world of theory. And I definitely became addicted very much. And thank you very much.